Welcome back. In this video, we're going to talk about matrix anatomy and built-in functions in MATLAB to take advantage of different structures within matrices. We'll begin with a discussion of what we call the main diagonal elements of a matrix. We say that the main diagonal elements of a matrix A are the elements with equal row and column indices. In other words, we say that AIK is on the main diagonal of A if I is equal to K. Let's take a look at a 6 by 6 matrix, which we see here on screen. Notice that each matrix entry has three quantities that we've talked about: the row index, the column index, and then the stored value at that address. Here in green on screen, we see highlighted all of the main diagonal elements of this matrix. A11 is a main diagonal element because the row index I equal 1 is identical to the column index K equal 1. So A11 is on the main diagonal. The same is true about A22, A33, all the way to the end, which is called A66. In just a few minutes, we're going to introduce some notation about calling this diagonal set of elements a band of this matrix. This is called the main diagonal band because it's a collection of all the main diagonal elements. In MATLAB, we have a special function for dealing with the diagonal elements of a matrix. That's called the diag function. Let's go ahead and type height diag. This allows us to create what they call diagonal matrices and also grab the diagonals of a matrix. There are a few different versions of syntax we can use to take advantage of the diag function. We're going to focus on this last one right now for this example, which is to input a matrix and then output a vector. Specifically, let's take a look at an example involving the 8 by 8 identity matrix. Here we go. If I now type in the diag of the matrix I8, MATLAB will pull off all elements along the main diagonal of that matrix. So this function says, take the matrix I8 and pull off all elements along the main diagonal entries. Let's go on to example 2 of how to use the diag function. To do this, let's go up to the help menu and type in gallery. This is a gallery of test matrices. We're going to scroll down until we find information about how to use the greatest common divisor for the test matrices. Notice we have a call A equals gallery of the matrix name GCD mat and then comma n, where this returns an n by n matrix. The individual entry in row I, column J is equal to the GCD between I and J. Let's go ahead and try this. So we go ahead and pull that syntax off. Let's define n here to be 10. So the greatest common divisor between 2 and 2 is 2. The greatest common divisor between, 10 and 5 is 5. The greatest common divisor between 9 and 3 is 3. So the entries of this matrix are the greatest common divisor between the individual row and column index. The reason I want to call attention to this is if we set D to be equal to the diag of A, this is going to pull off the individual diagonal entries along the main diagonal. The definition of the main diagonal entry leads us very naturally into a generalization of that, which is the diagonal bands of a matrix. We say a diagonal band of a matrix A that has m rows and n columns is a set of entries in which there is a constant difference between the row and column indices. In other words, if we look at any entry A sub ik, where I is the row index and k is the column index, if we take the difference between k minus I and set that equal to a constant, all entries that satisfy that condition for a specific constant are known as a diagonal band. So for example, on the main diagonal element, I1, K1, 1 minus 1 is 0. So we say that that is the 0 band of that matrix. Notice that forms an entire diagonal band because 2 minus 2 is 0, column index 3 minus row index 3 is 0, all the way to the end, 6 minus 6 is 0. We could go to a super diagonal band, one above the diagonal, by recognizing this is the positive 1 band, since column index 2 minus column index 1 is positive 1. Entry 2, 3 is also on that band, since column index 3 minus row index 2 is 1. entry 3, 4 is on that band. 4 minus 3 is 1, all the way down to 5, 6, because 6 minus 5 is 1. If we go one position over, this is going to be the positive 2 band, because remember, bands are defined by column index minus row index. The reason that they did that was they thought super is above, so that should be positive. Sub-diagonal bands are below the diagonals, that should probably be negative. In this case, we see that the -1 band of this matrix is all the entries directly below the main diagonal. Notice 1 minus 2 is -1, 2 minus 3 is -1, all the way down to 5 minus 6 is -1. The reason bands come into play is many applications rely on what they either call tridiagonal or pentadiagonal matrices, where we have special values along the diagonal bands of a matrix. Let's see how we can take advantage of this definition using the diag function. To do this, we're going to go ahead and investigate a new function that we've never seen, which is randi. Notice randi or randy produces pseudo-random integers from a uniform discrete distribution. In other words, it's going to populate a matrix with random integers. Few different calls. One of them is to say r is equal to randi, the maximum value of the integer that we want, and then the dimensions of a square matrix that we desire. Notice that matrix will contain pseudo-random integers drawn from a uniform distribution starting at 1 and going to the value of I max. Let's see what we mean by this. So if we put A equal to randi, let's say that we want this matrix to be populated with integers that are randomly selected from 1 all the way to 20. And we'll say that we want a 6 by 6 matrix. Notice that the entries of these can go from 1 all the way to 20, and this indeed is a 6 by 6 matrix. If we wanted to pull off the main diagonal entries of A, the ones equal to 1, 8, 3, 17, 10, and 8, remember that is the main diagonal band whose difference between the column and row indices are 0. One way to do that is just to type in diag of A, and it would pull off that vector. Another way to do that is to tell MATLAB specifically, please find for me the diagonal band whose difference between the row and column index is 0. Notice those two calls produce the exact same values because the default band is the main diagonal. However, I can actually use the diag function to pull off other bands of the matrix. Suppose we wanted to find the first super diagonal band, the one above the main diagonal. If I type in 1 here, MATLAB is going to pull off the diagonal band where the difference between the column and row index is 1. So here, this entry is 1, 2. 2 minus 1 is 1. That is on the +1 band of this matrix. Notice that band is exactly what we pull off. If I wanted to pull off the subdiagonal band right below the main diagonal, instead of a +1, I would put a -1, and that's exactly what we see. Notice the one right below the main diagonal is 19, 3, 19, 1, 11. That's the exact thing that I pulled off here. Of course, we could be a little bit tricky. Suppose I wanted to get this element in the matrix 6. Well, that is going to be the +1, 2, 3, 4, 5th band of the matrix. So if I type in diag of A and I go to band number +5, that's going to give me this element. If I go diag A -5, that's going to give me the -5th band below the main diagonal, which is just one element. Let's explore some other options in the diag function. Notice that we were just looking at how to pull off main diagonal entries from a matrix, but diag as a function does more than that. Specifically, we can input a vector into the diag function, and that will create a square matrix where the entries of that vector now line up along the main diagonal. Let's see what we're talking about here. Let's suppose that I create a vector 2s, which is a 4x1 vector that has all values of 2s in it. If I now put that inside the argument to the diag function, MATLAB is going to create a 4x4 matrix whose main diagonal elements are populated with the individual entries of my vector. Let's see a second example of how this works. So suppose that I create a vector A that is a 1x5, -4, -2, 0, 2, 4. If I now type diag of A, MATLAB creates a square matrix that has the individual elements of my predefined vector along the main diagonal of that matrix with all other entries equal to 0. In addition to allowing me to put specific vector values along the main diagonal, we can also put them along the diagonal bands of a matrix. So here let's define a set of -1 entries to a 3x1 vector. If I now type diag of -1s and I put that in the super diagonal entry, notice I put a +1 because the difference between the column and row index is going to be +1. I could also put that in the sub-diagonal entries by putting a -1. Using that structure, let's take a look at this line of code. So remember that the 2's vector is a 4x1 with all 2 values. The -1 vector is a 3x1 with all -1 values. Here I'm going to tell MATLAB, create a diagonal matrix whose main diagonal elements has all 2's in it, and it's a 4x4. Then create a 4x4 whose super diagonal elements has all -1's in it. Oh yeah, also create a 4x4 matrix whose sub-diagonal band, -1 band, has all -1's in it. And then add all those matrices together. We haven't seen a lot about matrix addition yet, but what I want to show you is when I hit enter on this, this allows me to populate a 4x4 matrix where the main diagonal elements are all 2, and then the super and sub-diagonal 1 bands have all -1's. It just so happens this is a famous matrix that shows up in something called finite difference mechanisms. The point of this example is to show you how to exploit the structure of the diag function to do some interesting matrix algebra. Let's keep going with our discussion of matrix anatomy. We've talked about the main diagonal entries of a matrix, which are the ones where the column and row index are identical. We've also talked about the diagonal bands of a matrix. Positive diagonal bands are the ones above the main diagonal. In other words, positive difference between column minus row index. Negative diagonal bands are below the main diagonal. In other words, the difference between the column index and the row index is negative. Next thing we're going to do is talk about the lower triangular entries of a matrix. We say that an element A sub ik is a lower triangular entry if it is on or below the main diagonal of the matrix A. In other words, we say aik is a lower triangular entry if and only if the row index is greater than or equal to the column index. Notice A31 is a lower triangular entry because the row index is indeed greater than or equal to the column index. A44 is also a lower triangular entry because the row index 4 is greater than or equal to the column index 4. The entry A26 is not a lower triangular entry because row index 2 is less than column index 6. In other words, 2 is not greater than or equal to 6, not a lower triangular entry. Let's look at an example of how to capture lower triangular entries of a matrix. Notice we're going to define a matrix A, which is a 5 by 5 matrix. This matrix is going to have 8 on the main diagonals, because look, this vector inside is a 5 by 1, which is 8 times all 1s. In other words, that's a vector of all 1s. In this case, we're using repeated references to diags plus addition. This little 3 dots is an ellipsis, which allows me to write code on the next line, but interpret it as a single block of code. So in other words, MATLAB sees, take this matrix and add whatever comes below this as the same line of code. When I run this code, MATLAB creates a matrix A, which is a 5 by 5, like we said. The main diagonal entries are all 8. The sub-diagonal entries go from -4, -2, -1, and 0. Super diagonal entries go from +4, +2, +1, and 0. Next, we're going to focus on pulling off the lower triangular portion of this. To do this, we're going to use a function called TRIL. In other words, triangular lower. This extracts the lower triangular part of a matrix. So if I type TRIL parentheses, whatever my matrix name is, that's going to give me the lower triangular part of that matrix. In this case, we have this matrix A that we just defined. Let's define L to be TRIL of A, notice that's going to pull off the lower triangular portion of this matrix. Just like the diag function allows me to focus on the bands of a matrix, so too I can use the same idea in the second argument to this function. If I say that L is equal to TRIL of A, comma, -1, MATLAB understands this as pull off all lower triangular entries all the way up to the -1 band of this matrix. That's exactly what I see. If I type -2, it's going to pull off all the lower triangular portions below the -2 band. Similarly, if I define that second parameter to be +1, it will pull off all lower triangular portions up through and equal to the 1 band of that matrix. That leads us to our next definition, which is instead of the lower triangular entries of a matrix, we're going to talk about the upper triangular entries of a matrix. We say that elements in a matrix are in the upper triangular position if they were on or above the main diagonal. In other words, if we look at a matrix element AIK, we say that's an upper triangular entry if K is greater than or equal to I. Notice the green band here is the main diagonal. The portion of the matrix highlighted in blue are called the strictly upper triangular portions, and then all highlighted elements make up the upper triangular entries of our matrix. Just like we had the TRIL, or the lower triangular function, we also have the TRIU for upper triangular function. This function allows us to extract the upper triangular part of a matrix. We could also do so with the band parameter. Let's take a look at how this plays out in practice. Let's go back to our 5x5 matrix defined by the bands that we had previously. If we then look at U equal to TRIU of the matrix A, this pulls off all upper triangular entries, including the main diagonal. Of course, I could use the second parameter after the matrix call. So perhaps I put in +1. This will pull off all entries in the upper triangular position above the main diagonal, or all the way through the +1 band of this matrix. That is exactly what we see here. We're going to end this video by looking at a function that helps you reshape matrices. In order to do this, go ahead and type help reshape. This function allows us to take a matrix of a certain dimension and turns it into a matrix of another dimension. As a challenge to you, I'm actually not going to show you how to do this, but allow you to read the documentation and figure out for yourself. Here's a great example of how this function works. If I go ahead and define a matrix from 1 to 10, and then I reshape that matrix A and turn the 1 by 10 into a 5 by 2, MATLAB produces a 5 by 2 and literally just goes column by column. I'll leave you to read through the other part of that documentation and look at other examples for yourself. We are now done with our formal lesson on how to use MATLAB to define arrays and to access elements of arrays using many built-in functions. A lot of this stuff will come into play later in this course as we learn how to code our own matrix functions, and we want to take advantage of MATLAB's built-in library to check our work. Keep up the hard work, and I'll see you in the next video.